Hi everyone, my name is Andrea Marchisio. I'm a last year PhD student at Politecnico di Torino. Today I will talk about my research regarding photonic integrated circuits for neuromorphic computing. But first, something about myself. I got both my bachelor's and master's degrees at Politecnico di Torino, where then I started my PhD, during which I authored two papers in scientific journals and 15 contributions to international conferences. As part of my PNRR scholarship, I also worked 6 months for Synopsys Incorporated in the Netherlands, and also I spent 6 months as a visiting researcher at the Eindhoven University of Technology. Photonic integrated circuits are becoming a key enabling technology in many different fields thanks to their inherent advantages, such as high speed, low power consumption, high parallelism, but also some more practical advantages, such as compatibility with CMOS processes and high integration densities that are quickly making them economically viable to the mainstream market. In this context, my research focuses on machine learning applications of photonic integrated circuits. Machine learning in recent years has been characterized by two main trends. The first being the fact that computational requirements to train a neural network have been doubling every 6 months, while in general, integration trends and therefore increasing computational power has started slowing down with respect to the past. In this context, photonic integrated circuits could offer an alternative paradigm for machine learning, both for the advantages that I mentioned before, but also thanks to their capability of implementing efficient matrix multiplications that are fundamental to train a neural network. Therefore, my research focuses on modeling, simulation, and measurement of photonic integrated circuits for neuromorphic computing applications. And in particular, we explored two main avenues of research. The first being the development of a comprehensive model for photonic linear neurons based on thermally tuned Mach-Zehnder interferometers, while the second concerning the measurement and modeling of all optical nonlinear activation units. Starting from the first, we can say that Mach-Zehnders are a popular choice to implement linear neurons, but unfortunately they are characterized by spurious thermal interaction between neighboring devices that cause a strong reduction in accuracy while training a neural network. For this reason, we developed a semi-analytical model that is able to simulate the normal propagation of light through the device, but also capture this spurious thermal crosstalk in order to create an instrument able to predict it and counteract it. We validated successfully our model by direct comparison with measurements of a 3x3 Mach-Zehnder interferometer mesh developed at the Denmark Technology University. Continuing on, we can say that another important challenge of photonic neuromorphic computing is the development of a power-efficient all-optical nonlinear activation function. During my stay at Eindhoven University of Technology, I had the chance of studying and measuring this device that you see on screen that is created with two Mach-Zehnders with a nested micro ring able to implement programmable nonlinear activation functions. This chip was developed on the cutting-edge IMOS technology developed at TUE, which is able to implement stronger nonlinear effects with respect to silicon thanks to the properties of indium phosphide, but also thanks to the confinement on a very thin layer of material. And studying this structure, we obtained multiple interesting results, but the most interesting one is the fact that we were able to implement a leaky ReLU function, which is one of the state-of-the-art nonlinear activation functions for traditional machine learning, without any power consumption. In conclusion, I showed you the potential of photonic integrated circuits to pave the way to next-gen devices for many different fields, but in particular for neuromorphic computing, thanks to their inherent advantages. I also showed you some of the results that we obtained when developing a model for linear neurons, able to capture spurious thermal effects. And I also showed you some results of our measurements of all-optical nonlinear activation functions, able to implement a leaky ReLU activation without any power consumption. Thank you for your attention.